So far we have seen the definition of quasi-projective variety, and they are in general. So before I just want to make the remark, yesterday's remark again, that you have this quasi-affine which is inside affine. Now point is this, this you can think as in quasi-projective, and here you have some projective. Why? Because you have this ui which is a open subset in Pn, and you have some affine space, and you have some homeomorphism phi I, right? So if I take some open subset here, so if I take a quasi-affine variety, so that means it's some open subset here, and then this phi I is a homeomorphism. So this phi I will send this u to some open subset of ui, but this ui is open in projective variety. So that will say that phi I of u is open in Pn. So it's a quasi-projective variety. That's how a quasi-affine is you can think as a quasi-projective. Sorry, yeah, sorry. Yeah, yeah, quasi-affine. This is. So affine, of course, is sitting inside quasi-affine because affine varieties are open in affine. I mean, any, right? But now quasi-affine, they are sitting inside quasi-projective in this way. So if you take an open subset here, so you apply phi I because phi I is a homeomorphism. Okay. So now, so this is, but still some problem in the sense that this when you define quasi-projective, it is an open subset in some Pn. But now the question is that if you take another n, will they give you the same variety? So it's an embedding problem. So it still depends on embedding. So, but if you want to do a very concrete, anything concrete, so you should have some coordinate free. You should not depend on some embedding, because when you put some embedding, it is in some projective variety, it becomes restrictive. So point is that can one give a coordinate free or can one give a abstract definition of quasi-projective variety or more general varieties? So this is not abstract because it is in some projective space. Can one give more general definition? Of an algebraic variety. That means it should not depend on any integer or anything or any embedding. So the yes, answer is yes, and that is called pre-variety. So it is very similar to the construction of scheme, but at the variety level. So the answer is yes, and that's the definition of what is called pre-variety. Huh?
We are talking for quasi-projective and projective.
Yes. But can one define algebraic variety means can one define more generally, like this is a quasi-projective is some open subset in Pn. Can you generalize this definition? See, the problem with quasi-projective or quasi-affine means there is some open subset in some affine space. Abstractly, like when you say topological space is a very abstract definition, right? It does not depend on whether it is in Rn or in Cn or anything. It's just a definition. It's some set with some condition, some set. Similarly, can you give such definition of an algebraic variety? I mean, algebraic variety. So that affine variety, quasi-affine variety, projective variety, quasi-projective variety will fall into pieces. Yeah. Then because then when you define, so for example, when you do topological space, a map of topological space, it's an abstract map, right? Similarly, we want to do a map of algebraic varieties. I don't want to put it inside some AN or CN or PN and then do the calculation, because you may have two things, they may look different, but they are isomorphic. They may one variety, suppose it is in P1, suppose X is equal to P1, but you can embed it into some higher projective space. So, but this P1 and that image, they are in two different space, but they are isomorphic. So we don't want to differentiate them. See, up to the point is that you want to classify spaces. Like if you, the ultimate problem in topology is that you want to classify, means up to homeomorphism can you classify. When you study group theory, the first question was for finite groups, can you classify groups? If I give a n, can you classify groups of, say, abelian groups or any finite groups of that order? So it is like a classification problem. So classification up to what? Isomorphism in group. Similarly, here you don't want to differentiate two varieties which are isomorphic. But so what I am saying, this P1, if you embed it into Pn, this may look different. It is in, because it is in some another projective space, but it is actually a copy of P1. So you don't want to differentiate this P1 and that's how the image of that P1, because they are isomorphic. So the point is that, so that is the reason. So you should not, so it should be embedding free definition, because the two different variety may be isomorphic, but they are embedded into some different space. So it is difficult to check whether they are isomorphic. So when I say abstract variety, means it's a abstract variety. It may be isomorphic to some variety which is embedded into some projective space. It's fine. So this is the advantage of doing giving the definition. So one should give definition like a topological space. When we give a topological space, mostly we give some examples, then you embed it into some Rn or Cn and give examples. But when you talk about abstract topological space, just X is a topological space. Similarly, can one define algebraic variety in that sense? That was abstract affine variety. But now you want to include the projective varieties also. That way you cannot define projective varieties. Quasi-projective varieties, so everything you should include. So whatever I have done so far, these are all examples of varieties. These are not a concrete definition of a variety. So now I am going towards that. How to define a variety, abstract variety. This is called pre-varieties, and some books Mumford calls pre-variety. Okay. So to define pre-variety, I need to introduce some notations, like now some more terminology. Basically, sheaves. I need to define what is called sheaves. So if you see the manifold, when you define, if you have some knowledge in differential geometry or differential topology, how did you define your manifold? It was something like you have some atlas, right? Some U alpha and some phi alpha. So if it is a topological manifold, then X is union of U alpha, and these U alphas are open in X. And these U alphas are homeomorphic to some copy of Rn, right? Or Cn or whatever. And this now if it is a topological manifold, then phi alphas are homeomorphism. If it is a differentiable manifold, then this is a biholomorphism. Or these are phi alphas are C infinity differentiable. And if it is a holomorphic manifold, then these phi alphas are biholomorphism, right? Inverse, yes. Bi means both way. So now the point is that this, now I want to define abstract algebraic variety as union of something, and these U alphas are the models are local models. So these are local models. Rn is a local. So the differential structure on U alpha or the holomorphic structure on U alpha is induced from this Rn or Cn, right? That's how you get the structure, algebraic structure or differentiable structure on a manifold. You pull the structure through these phi alphas. So now point is that now we have so abstract variety locally looks like this U alphas are affine varieties. Locally they look like a affine variety, and this x, the abstract variety is affine variety. That is the affine variety is a very much coordinate free definition you have. It's a finitely generated K algebra basically. So that is a very abstract definition. Affine variety is fine. So the abstract variety locally looks like a affine variety, and you need to glue these affine varieties. So you need to know. So that's the sheaf data. Okay. So this is the motivation to do this sheaf theory or introduce this because you want to define more generally what is an algebraic variety. So I'll.
So what will like first term, second term correspond to here? Like manifold is first term and second term.
Yeah. So here we have them separatedness, separated algebraic variety. Hausdorffness is condition is called as separated. So we will consider mostly separated algebraic variety. So there will be some conditions. Yeah. Diagonal is closed. If you take x and then there is something called x cross x, product of variety. So then if the image is closed under a diagonal map, then you say it's a. So those things will come on proper. This is a separatedness. Yes, this is called separated. Yeah.
That is not like usual.
See, topology is so bad. It's not Hausdorff because if you take any irreducibles, any two open set, they always intersect. See, in Rn, the good about this topology is that if you take a point x and y in Rn, then you can differentiate these 2 points by 2 different open subsets. But in affine variety, the open sets are quite big. So they will always intersect, they will be not disjoint. So it's not Hausdorffness is not a good condition for Zariski topology. But separatedness, where there is something called separatedness, that is the analog of Hausdorffness in the variety case. Yes. Open subset of irreducible is always dense. Anyway, so the topology is little peculiar in the sense that there are not many open subsets, small. So that's why something is called completion. So when you do completion of a ring, then you get a small open subset. So if you want to study analytical study, analytical. So sometimes you have to consider those open subsets, but it's a small open subset. They are not Zariski open. They are called yes, it's called completion. You have to take the completion. Analytic sense, in the analytic sense, it is an open subset. So those things are there. So, but anyway, let's not go into such those details. Okay, now. Sometimes you call Etal topology. So these are more refined topology. Zariski topology is a very coarse topology. It's not a fine topology. But it's very natural. It comes with commutative algebra. I mean, it comes naturally with commutative algebra. So that's why it's useful. But sometimes these open subsets are too big. You cannot work with those. You have to. So then you have to work with Etal topology or completion. So those things are there. Okay. So let's define what is. Sheaf of abelian groups or presheaf and sheaf. So this is a very general definition for any topological space you can do, nothing to do with algebraic variety. So, point is that now we want to give a embedding free definition of algebraic variety. Okay. So, this is the goal. That is why we are now we will whatever we want to do is. So, X suppose is a topological space. A presheaf. So, presheaf you can talk about presheaf of sets, but mostly we will work with presheaf of sets is not a very good thing. You work with some structure. Presheaf of abelian groups. Abelian groups are most simple objects, right? Z module. So, presheaf of abelian groups. So, how do you define? So, it is a data that for every open subset so F is denoted, F is called presheaf, Fu is an abelian group. Now if U is empty, you define Fu to be the identity group, the 0 group. If it is non-empty, it can be some abelian group. Now the condition is that if you have some, say, U is a open subset of V and V is a open subset of X, then you have F of V and F of U, these two abelian groups. So, one can restrict, so there should be some restriction function, and this should be a group homomorphism. Okay. Now, if you take U, V, W, say these are all open subsets, then F, V, so sorry, now here you have a map from FW to FV. So, if you go F, so W also contains U as a open subset. So, if you go by FW to FU, there is some another restriction map. So, if I call this is restriction of W V, and if I call this is VU, if I call this is WU, then the condition is that this diagram should be commutative. That means that res VU composition restriction of W on V, it should be restriction of WU.
So these open sets are with respect to induced topology.
Yeah, X is a topological space, so open subset. U is an open subset.
In V, V has the induced subset topology.
Yes. Or you can think that U and V are open subset of X, U is a subset of V.
That's the thing.
This is, I mean, we could have said that U, V such that so this is so point is that for every open set you associate a abelian group, and if you have a restriction map. So, if you have an open subset of this, then you have a restriction map. It is more like you can think as if you have a functions, continuous function. Suppose X is a topological space. So, examples, let us see some example. So, you take X any topological space and you take any open subset. So, define the shapes, say C x u. So, these are all continuous function, f is continuous, where this is a C is a topological space in this analytic topology. C has a topology, C is a topological space. In particular, if I take any abelian, suppose A is any abelian, then of course this is a, if you have this restriction function, right? If you take a continuous function, then if you restrict on a smaller open subset, that is also continuous. And then the diagram also is commutative. If you further restrict to another smaller open subset, so restriction of another restriction is the restriction of the smallest one. So, if you take a abelian group, say abelian topological group, then you could have taken say C x a valued. So, this is nothing but set of all function from u to a, f is continuous. Instead of C, you could have taken any abelian topological group. The abelian, because I want these groups to be abelian. If it is taking value in abelian, something abelian, then you can sum and multiply, and that will remain abelian. So, that is why I am saying abelian. Okay. So, these are, and instead of topological space, you could have taken X to be differentiable manifold and take F to be C infinity functions, or you could have taken holomorphic function. So, all these are all for examples of Presheaves, but there is something more. So, Presheaves more, so something, a Presheaves is called a sheaf if it satisfies additional two condition. Sheaf if following two condition it should satisfy. See,
the restriction between the abelian groups. For example, if you are choosing two open sets which is contained in one each other, U is contained in V. Then f of V to f of U, we are having that restriction. So they both are abelian groups. What kind of map it is?
group homomorphism. When you are in the category of abelian groups, this morphism should be abelian group homomorphism.
We are just giving the name restriction.
Name is restriction, yeah. You could have instead of restriction, because mostly when we work with this kind of things, these are restriction maps, because these are some functions, regular functions or continuous functions, or so your restriction easily makes sense there. So, this instead of this we could have written rho WU. Some other group which satisfies this part, that is also a Presheaves. And sometime, okay, let me define what is a Presheaves. A Presheaves is called sheaf if you take U open subset X and U has a cover, say union of U alpha, open cover, and suppose S alphas are sections. So, element of the this group, these are called sections sometimes. You will see why they are called section when I give some examples. These are called section. If you have S alpha in FU alpha such that S alpha restricted to U alpha intersection U beta equal to S beta restricted to U alpha intersection U beta. So, when I said this means that restriction of U alpha And by this I mean restriction of u beta so this is if this happens, then there exists a unique S in f of u such that S restricted to u alpha is S alpha.
So the above S alpha and beta is for all S alpha and beta.
Yes, yes, yes. And for every open cover, when I write U is union of U alpha means any cover. When I take a element S alpha means any S alpha. So those are for every S alpha, for every, so you have a open subset, you could have taken X also, but U is any open subset of X. And if you have a cover U, if you can open cover, so basically it is like a patching. If you have a continuous function, if you have some function on U, or if you have an open cover of a set, and you on each cover you have some function which are continuous, and if they are restrict to, when you take a intersection, each intersection, if they coincide, then you can patch them and make a function on the whole. So it is the same, this is all patching condition. But the point is, it should be unique. There should not be another function which should satisfy this. So this is if I decode this again, I mean this is equivalent of saying that so uniqueness I can decode. So first of all, there exists S such that if S alphas are dot 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 like this, U is union of U alpha and S alphas are in F of U alpha such that S alpha are restricted to U alpha intersection U beta equal to S beta, U alpha intersection U beta. Then there exists a S in F of U such that S restricted to U alpha equal to S alpha. Now, the uniqueness says that uniqueness is same as saying that this is the condition 1, and uniqueness will say that if there are two such S and T such that S restricted to U alpha is same as T restricted to U alpha. So, if you have a section over U, the bigger open subset, such that if you restrict to each U alpha, they are same, this will imply that A is equal to T. Because S restricted to U alpha, if you further restrict to U alpha intersection U beta, and T if you further restrict to U alpha intersection U beta, they are same. So, and the uniqueness is saying that if I have say S and T, which satisfies this property, is same as saying that A is equal to T. So, this is the condition 2 is the decoding the uniqueness condition. Or this is also equivalent of saying that if you have something, some S in F of U such that S restricted to U alpha is 0, implies S equal to 0, where you take the section S minus T. Since this is a abelian group, S minus T makes sense. S minus T restricted to U alpha is nothing but S restricted to U alpha minus T restricted to U alpha, which is 0. So, these are all equivalent conditions. It's like injectivity. When you say group homomorphism A to B, F of X equal to F of Y, it is injective if and only if it sends, if it is 0, image is 0, then it has to be 0. So, it is the same. So, these are all equivalent sheaf condition. So, a pre-sheaf is called sheaf if they satisfy this gluing condition. This condition is called gluing condition.
Is there two
Yeah, I mean how you look at it. If you just say this is the condition, then there is only one condition. If you say there is a unique, but then you can break it into these two, 1 and 2. There exists a section, and then if there is 2 section, then they are equal. So it is how you look at it.